Okay, in this short tutorial what we're going to look at is the universal wave equation. We'll look over a couple examples as well, and then in the second video we'll look over a few more periodic wave examples that use the universal wave equation. So the universal wave equation is a fantastic equation. It is this equation that, as it says here, it's like how do we relate the speed of a wave to just its wavelength and the frequency of the wave. Now what's really cool about this is that the wave equation talks about the speed of a wave. And when we talk about the speed of the wave, and we're going to be relating it to the wavelength and the frequency, it becomes for a wave for us to describe not only mechanical waves, but light waves and matter waves and all these other things that exist in physics and chemistry, that it gives us this opportunity to really discover how the wave behaves and how we can predict where it's going, and based on the frequency and the wavelength, how fast it's moving through some material medium, or if it's light through through empty space, it still travels at a very specific speed. So the speed of a wave is just going to be given v, the symbol v. The wavelength, as we saw before, is for periodic waves is lambda, and the frequency is f in this case. Sometimes it's nu, but we're going to write it as f in this case. So the variables that are at play here are speed, frequency, and wavelength. Okay. Now I've just shown a very simple periodic wave right here. Now if we're talking about a mechanical wave, this mechanical wave is propagating through some material medium. It's transferring energy through the medium, and it does so at a very specific speed, and that speed is dependent on the medium that you're in. Okay. And the wave energy moves. We know the particles, because this is a transverse wave, it's moving up and down. The particles don't actually move with the wave, they just move up and down, and they move at a specific speed because the energy is passing through that wave. We know that we've got our rest or equilibrium position here. The amplitude of the wave is given by the rest position to the top or the rest position to the trough. Okay, and this here is our equilibrium. Alright, so let's start developing this wave equation. Now, one thing you'll need to recognize again is we need to talk about the wavelength. And so for one cycle to occur, so let's say we start at the top here. For one cycle, we get to there. If we measure the distance from crest to crest in this case, that will tell us the wavelength. Now, regardless of where we pick the point on the wave, I could pick this point here. Well, one cycle from here is right there. That's where the wave starts to repeat itself again. So the time to do one cycle is called the period. The number of cycles that occur in one time unit is called the frequency, and the distance, horizontal distance in this case, from that point to that point is the wavelength. You'll notice that from crest to crest, or even easier from trough, or as easy, trough to trough would be the wavelength, or at any point we can always find the wavelength. That could be from here to here, for instance, so that distance could also be measured as the wavelength. Okay, well, we're going to recall some things to help us do this. Now, what we're going to recall is that the speed of a wave is always constant as long as the medium through which it is traveling remains the same. So, speed is constant if the medium stays the same. The speed will change if we change the medium or the properties of the medium, but it will remain the same regardless. Alright, so going back to kinematics, we talked before about something called average speed. Now the average speed equation, what we can get from it, if we want to figure out how far a wave has traveled, the distance, or sorry, not a wave, but just an object has traveled, we simply take its velocity and you multiply it by its time. So I'll use in fact, if we don't want to talk about velocity, we'll just talk about the scalar units. We could say that distance equals speed times time. You're like, okay, easy enough. Meters per second times seconds gives meters, kilometers per hour times hours gives kilometers, so we get distance units. Alright, now we're going to do a little analogy here. Okay. what do we call the fundamental distance unit that a wave travels for a wave? Okay, so if we talk about the fundamental unit of measurement for a cycle, the distance through which a wave travels in one cycle, or so 1 unit of time, in this case here, right? Or from here. We can see that that distance unit, the distance that the wave travels if it's moving at some specific speed, so this crest would be like, it would go down, but you'd see it moving this way if you can imagine the wave propagating this way. So this distance that it travels is the wavelength. So that's the analogy that we're going to use. So in this case, we're going to say that the distance the wave travels is called the wavelength. Now, the time, so the delta t, so we got the distance is the wavelength. Now this time here. Well, what is the time interval for the wave to go from here to here? Well, from the wave to propagate and just move this far at some speed v, we knew that that was the wavelength. Well, that's one cycle. Well, how long does one cycle take? One cycle takes one period of time, t, that we learned before. Now the speed, the analogy for speed is just speed. And so what we end up with, what we get out of this, is something really interesting. If we replace d with lambda, and we replace the speed with speed, and we replace the time interval with the period, we get lambda equals v times t. Now this could be one way of relating these two variables. However, we're going to make a couple of changes to it so that we can get what's called the wave equation. This actually works. I call it the TV equation because you can just swap these two and call it TV. So lambda equals TV. It's a stupid joke. So what we're going to do from here is we're going to look at what period is. Okay, and period, we recall, is just simply the reciprocal or the inverse of the frequency. So if I do a quick little replacement here and a little substitution where I know that the relationship between period and frequency is period equals 1 over frequency, I can substitute that in right here. Okay, so what I get is lambda equals v times 1 over f, which is just v over f. Alright, so I've got lambda equals v over f. If I multiply the f up here, so I multiply both sides by f, I get lambda f, like so. And all I do at this point is we just change the way it looks a little bit. So speed equals, because whether you write 2 times 3 or 3 times 2 for a scalar product, whenever you're multiplying scalars, it doesn't matter. So you can do lambda times f or f times lambda. We tend to write it like this: frequency times the wavelength. So the wave equation is simply written as v equals f lambda. So from here we know that this is the speed of the wave, so v is the speed, and the units for the speed are typically meters per second. You can have other units, but for now we'll just say it's meters per second. F is, of course, the frequency measured in hertz, or we know hertz is cycles per second, or 1 over seconds. And lambda is the wavelength, and that's measured in meters. And so if you look at the unit analysis, everything works out nicely. On the left hand side we have meters per second equals frequency is 1 over seconds times meters, which is meters per second. So the units check out perfectly. So let's actually look at some problems and some questions that involve the wave equation, v equals f lambda. Okay. So the examples that we're going to look at are, oh, here they are. From the package that you have, we're going to look at these quick examples right here. So it says the wave below represents a wave that undergoes 30 cycles every 9 seconds. Okay? Calculate the frequency and period of the wave. Alright, so here's a wave, and it's doing 30 cycles every 9 seconds. So what we're going to do is we're going to say the frequency, like so, is cycles over time. So we have 30 cycles over 9 seconds. So we can do 30 divided by 9 is 3.33 cycles per second, which is a hertz. Okay. Period is 9 seconds. It takes 9 seconds to do 30 cycles, which is 0.3 seconds. So it takes 3.3 seconds to do one cycle. So you could write it as cycles per second. So sorry, seconds per cycle. So it would take 0.3 seconds for every cycle, or 3.33 cycles per second, which is the hertz. Now you could have, if you have the frequency, right, there's multiple ways of getting this. This could have also just been done as 1 over f, which is 1 over 3.333 repeated, and you would have got 0.3. You get the exact same answer. Or if you knew the period was 0.3, you could have found this by doing 1 divided by 0.3. Okay. It says use a ruler to measure the amplitude. Well, the amplitude of a wave in this case is from here to here. So the amplitude equals, okay, I'll just take my ruler. I'm going to be very rough with these, just you can make your measurements better on your sheet. 2.1 centimeters. Is the speed of the wave dependent on the amplitude? The answer is no. It is amplitude independent. It's only the material medium that it's traveling through that matters. Measure the wavelength. Alright, I'll do it from trough to trough just to change it up. So this is my wavelength here. Okay, so I'm going to use my ruler, and I will measure it to be, let's see, 2.3. So 2.3 centimeters is the wavelength. Okay. It says convert the measurement to centimeters. I've already got it in centimeters. Calculate the speed of the wave. That probably is supposed to say meters. So the speed of the wave is the frequency times the wavelength. The frequency in this case is 3.333 inverse seconds, or hertz, times the wavelength, which is 2.3 centimeters. So if we do 3.3333 times 2.3, we get 7.7, it's like 7.6666 centimeters per second, or 0.077 meters per second, because we know there's 100 centimeters in a meter. So there you go. So you're able to calculate from a graph. If you have some information, you can actually figure out the speed at which these waves are going to be traveling. It's very straightforward. So let's try a different one here. So the wave below is traveling through the same medium, oh interesting, as the wave above. State the speed of the wave. Well, I actually gave it away, part D from above. Since the speed, the medium isn't changing, this thing is still moving at 7.7 centimeters per second. Now remember, it was actually 7.66666 centimeters per second. Just we'll keep the more accurate version of it just for now. Measure the wavelength. Oh, look at this one. This one, the wavelength has gotten bigger. You can see that from here to here is larger than in the previous question. So what you should notice is that if the wavelength is getting bigger, something should happen to the frequency because the speed of the wave is staying the same. So let's measure. I'm going to measure it from the trough, even though I wrote it at the top, just because there's something in the way for my ruler. This is about, looks like 3 centimeters. Calculate the frequency. All right. Well, in this case, V equals frequency times the wavelength. Now if we rearrange for the frequency, it becomes frequency equals V over lambda, 7.666 divided by 3 equals 2.6 hertz approximately. Okay, so you'll notice something. For this second wave, as the wavelength got bigger, it implied that the frequency became smaller. So an increase in the wavelength caused a decrease in the frequency, because the frequency went from 3.33 hertz down to 2.6 hertz. This here, put a big star, highlight it, whatever you're going to do, is some big learning here for this. If the material medium does not change and the speed must stay constant, now this is really important when we start talking about light and things like that. If the equation is V equals F lambda, if V is to remain constant for a given medium, then what this means is that if the speed is going to stay the same but the frequency gets really big, then it means the wavelength must get really small. Or if the speed is the same, if the frequency gets really small, the wavelength must get really big. So it's always this relationship where an increase in the frequency causes a decrease in the wavelength, and vice versa. This is a really important thing to note. So this works with light. If we increase the frequency of light, we know that we get really, really short wavelengths. If we decrease the frequency of light, we get really, really large wavelengths. And that's because the speed of the light must stay constant. And this works for waves as well. Now, a way to think about it is that if the wavelength gets bigger, if you imagine the wave striking your finger at some very particular speed, in this case the speed, we know what the speed is. So if these fingers, like if this is the wave here and then it has to move and hit your finger so that the wave hits you, then you know that if it's taking longer distance to travel, they're going to hit you less frequently. So as the wavelength's bigger, the frequency drops because they're hitting you less frequently. Whereas in the previous example, the wavelength's shorter, and therefore because it's moving at the same speed, the waves are going to smash into your finger or hit your finger at a higher frequency because it happens more frequently at a higher cycle per second rate. So that's one way to think about it intuitively as to why the relationship is this increase in frequency causes a decrease in the wavelength and vice versa. But that's a really important point to note in this work. Thank you. We're going to move on to the next one, which is 3 examples related to periodic waves and the universal wave equation.